Okay, so today we have a really fun video, something I've wanted to do for a while, and we're going to use SymPy to do some fun mathematical operations. And I do mean fun, right? We're not at math and physics fun with Gus to not have fun. So let us start first by importing SymPy as SP. Import SymPy as SP. Now I'm going to do this. You don't have to do this, but from SymPy, import this. And what this is going to do, this is going to allow me to use the functions that SymPy has defined without SP before that. So I can just say symbols, right, instead of sp.symbols. And since we're only using SymPy throughout this Jupyter notebook, it's going to simplify my life a lot. So I suggest you do that too. And if you want some LaTeX printing, which is what I love LaTeX, do init or sp dot if you didn't import this. So we're gonna do init printing. That's gonna print LaTeX. Init printing. Of course, I spelled it wrong. Okay. Now we're gonna set up our first equation, and what we're gonna do is we want to set up this equation. So we first need to make x a variable. And to do that, we can use SymPy's symbols, where x equals symbol for 1, so symbol x. Now, if you wanted to do, for example, let's say you want to do x, comma y, comma z, you have to do symbols, the lowercase s and the s at the and the s after l, and then you just do this. You do x, comma y, comma z. Now we want to set up our left-hand side of the equation, and that's going to be 3 times x squared plus 4 times x plus 2. Right-hand side, which is just 0. And then we can use equation, right, is equal to, eqn is equal to, equation. So this is equation for SymPy. So you can define equations. We're going to do left-hand side, comma, right-hand side. And then we're going to display equation so we can see if we did it right. And let's see if our equation looks good. That looks good to me. And then we're going to use solve. And we're going to solve our equation for x. So let's see what we get. Look at that. We get imaginary numbers. So we get 2 complex numbers. And we get our first one is in the third quadrant. We have this much, well, without the I, down in the imaginary axis. And we have negative 2/3 to the left of the x-axis. And then we get the same distance in the x-axis, or the real axis. And then you get square root 2 divided by 3 upwards in the imaginary axis. So that's really it. There's not much more to that. You can change this around, and you can play around with the equations you get. But, you know, you pretty much get the basics, and there's not much more to it. Now let's do this. We want to do this. So let's, again, use symbols. We want to use, let's use G for gamma, K for K, and M for M. We'll let that equal, and T, because we have, these dots are respective time. So 2 dots means the second time derivative, 1 that means the first time derivative. We're going to do T, and it's going to equal symbols. And we're going to do R before that, and that's just going to allow us to use LaTeX in here. So we're going to do gamma. So G is going to refer to gamma, which is just this Greek letter. We're going to do K, comma M, comma T. And then now we want X to equal function. So we want it to be a function now, because it's going to be a function of T. So X and T. So let's see if we put X, should give us, yep, there we go. So we get now a function of T. Now we want to set up our differential equation. And to differentiate, so we want ODE, which is an ordinary differential equation, to equal diff x comma t comma t. So that's going to be a second derivative. X, derivative with respect to time, derivative with respect to time. And you can do third, fourth. I'll actually show you a third one. We'll do that after. And we're going to do G times diff x comma t. And do plus, just fix that, plus K divided by M times X times X, left hand side, And again, we're going to do right hand side is equal to 0. But we don't actually need that. And let's display our OHS. All right, so we get kind of organized it weird, but this, then we have this. Now let's do equation EQN equals EQ left hand side ODE left hand side because that's how we defined it, comma, and that is it's a homogeneous, so it's equal to 0. And now we can display equation QN DE. Let's see how this looks. Okay, so they kind of messed up the order a bit, but nonetheless it's the same equation. And we see that we get a gamma over here for G, which is nice. So now we're going to use we're going to use solve, and we need to use dsolve, which is differential equation solve. We want to solve for x. All right. So we see we get a dampening, we get a falling off, we get the imaginary. So this is not how you. So you have to convert the what's it called? So we're going to get imaginary number because if we get rotation, it depends on the dampening. So you have to look inside. You see if this inside is less than 0, you're going to get an I. You get an I, you can convert that to cosine theta plus I sine theta. And you get the same thing over here. You have to do the same thing. Thank you guys so much for watching. I really appreciate it. Please leave comments. Thank you guys so much.